Hi, my name is Bahadur Ahmedov. In this video lecture, we are going to discuss about the homogeneous system of linear equations, its solutions, and also we're going to talk about something which is called the augmented matrices. So if you remember previously, we talked about the linear equation, and we defined a linear equation in the form of uh, a11x1 plus a12x2 plus and so on plus a1n xn is equal to the b1, where x1, x2, and so on xn are the variables of this equation. So the variables, and a11, a12, and so on a1n are going to be the coefficients of those variables. Coefficients of those variables, and the b1 is going to be called as the free coefficient because it is free from the variable. So whenever we have not one equation, one linear equation, but we are going to have, let's say, k linear equations, it is going to create a system. So we are going to write down the second linear equation in the same notation. So it's going to be a21x1 plus a22x2 plus and so on plus a2n(xn) is equal to the b2 and so on. A k1 x1 plus a k2 x2 plus and so on plus a kn xn is equal to the bk is going to be called as a system of linear equations, system of k linear equations, system of k linear equations. So this is called as a system of linear equations because the solution of one of the equations is going to be the solution of all the other equations. So essentially, we are going to denote the solution for the system of linear equations as x bar is going to be the vector within components, right? So the values of the x1 bar, x2 bar, and so on xn bar, so that if I substitute this vector to the first equation, to the second equation, to the third equation, or to any of the k equations, for all of the equations, this vector is going to be satisfied. Essentially, if I just substitute them instead of x1, x2, and so on, xn, the left-hand side of those equations are going to be equal to the right-hand side of those equations. So let's try to do an example and try to understand what does it mean, a solution vector of a system of linear equations. So we are going to talk about a system of two linear equations with the two variables. So let's say a system of linear equations is given as x1 minus 2x2 is equal to the 1. 3x1 plus 2x2 is equal to the 11. So this is a system of two linear equations, and the solution vector to the system of linear equations is going to be equal to 3 and 1. So what does it mean is that if I just substitute this to the first equation and to the second equation, it is going to be satisfied for both of these equations at the same time. So let's just substitute this to the first equation. It's going to be 3 minus 2 times 1, which is equal to the 1, which is true. And if I just substitute this to the second equation, it's going to be 3 times 3 plus 2 times 1, which is going to be 9 plus 2, which is 11, which is also true. So it means that this vector is going to be the solution vector to the system of linear equations. So now let's talk about a homogeneous system of linear equations. Whenever we are dealing with the system of linear equations where all of the free coefficients are equal to the 0, then this kind of system of linear equations is called homogeneous system of linear equations. So basically, notation-wise, it's going to be a11x1 plus and so on plus a1n xn is equal to the 0, and so on, a k1 x1 plus and so on plus a kn xn is equal to the 0. So you see for all of the right-hand side part, we've got the 0. So this kind of system of linear equations is called a homogeneous system. Homogeneous system. So the homogeneous system of linear equations are really important because later on we're going to talk about constructing the solution spaces for system of linear equations. And in order to construct such a spaces, we would need the solutions of the homogeneous system of linear equations. So one thing which I noted from here is that any homogeneous system of linear equations has the solution. And this solution is simply all of the variables, so x1 is equal to the 0, x2 is equal to the 0, and so on, xn is equal to the 0, is simply the solution. So please note that this is not a solution for any system of linear equations, right? So this is a non-homogeneous system of linear equations, so non-homogeneous. So non-homogeneous means that at least one of the three coefficients on the right-hand side part is not equal to the 0, right? So if you just substitute 0 and 0 instead of x1 and x2, on the left-hand side you will have 0, and on the right-hand side, which is equal to the 1, which is false, right? So you see, so this 0 solution is always true for the homogeneous system of the equations. So we call the solution when x1 is equal to the xt is equal to the xn as the trivial solution. Trivial solution. So it appears at the same time a homogeneous system of linear equations might have a non-trivial solution, which basically means that at least one of the variables is not going to be equal to the 0. But if a homogeneous system of linear equations has a non-trivial solution, it's going to have infinitely many solutions. So this is an important theorem which we're going to write, state, and try to prove. Theorem about the number of the solutions of the homogeneous system of linear equations. Any homogeneous system has either the unique solution, and we know what is the solution, right? So the solution is actually the trivial solution. Or it has infinitely many solutions, or it has infinitely many solutions. Okay, there is no other case. So either it has just a trivial solution or infinitely many solutions. The infinitely many solutions, if a system of linear equations, a homogeneous system of linear equations, has a non-trivial solution, then it is going to have infinitely many solutions. So let's try to prove this theorem. And then we're going to do an example, try to understand what does it implies. So let's assume, so let x1 is equal to the x1 bar, x2 is equal to the x2 bar, and so on, xn is equal to the xn bar is a non-trivial solution, for the homogeneous system. Of linear equations. So let's assume that our system has just one equation, right? So basically, I've got a system, a11x1 plus a12x2 plus and so on plus a1n xn is equal to the 0. So this is a homogeneous system of linear equations with one equation and n variable. So what does it mean that this vector is going to be the solution of this system? It means that if I just substitute the values of the x1 to be equal to the x1 bar, x2 to be equal to the x2 bar, and so on, xn to be equal to the xn bar, the left-hand side of this equation is going to be equal to the right-hand side. So essentially, so a11 x1 bar plus a12 x2 bar plus and so on plus a1n xn bar is equal to the 0. Okay, so a non-trivial solution actually means that at least one of the x1 and so on xn, at least at least one of the variables is not 0. It is possible that all of them are 0 except just one. So even in this case, the system is going to be called as a non-trivial. So if this is a solution of the system of an equation, then x1 is equal to the x1 bar times the t, x2 is equal to the x2 bar times the t, and so on. Xn is equal to the xn bar times the t is also the solution. Is also the solution of the system of linear equations. Okay, for any value of the t which is from the real number. So how many values of the t we can assign, how many real numbers actually we have. So infinitely many, right? So that is why we can create infinitely many solutions by just multiplying the solution vector to some t, to some real number. And this is going to be still a solution. How we can check whether this is a solution? So essentially, I just need to substitute this to the first equation and to the left-hand side, and need to show that this is going to be equal to 0. So let's try to substitute this. So a11 x1 bar t plus a12 x2 bar t plus and so on plus a1n xn bar times the t, right? So let me take out all the t's from all of the equations. So this is equal to, you see, so all of the terms of this equation have the t. So I'm going to take them out from the brackets. It's going to be a11 x1 bar plus a12 x2 bar plus and so on plus a1n xn bar. So if you look to this equation, so let's call this as a star, the equation star. So according to the star equation, so this is again the star, right? This is equal to the 0 actually, okay? So the 0 times to any constant is also going to be 0, okay? So that is why this vector is going to be the solution of this homogeneous system of linear equations. So essentially, if the homogeneous system of linear equations has a non-trivial solution, then it's going to have infinitely many solutions. So let's try to do an example, try to understand this more deeply. So an example. So let's say I've got a system of linear equations, x1 minus 2x2 is equal to the 0. 2x1 minus 4x2 is equal to the 0. So I've got two equations in my system of linear equations with the two unknowns. So can you guess that, the first solution which comes to my mind is going to be simply 0 and 0, right? If you just substitute the 0 and 0 to both of the equations, they're going to be true. And the second solution which comes to my mind, actually, which is the non-trivial solution, is going to be 2 and 1. So this solution is called the non-trivial. So this solution, when all the components are equal to the 0, is called the trivial solution, right? The non-trivial solution means that when at least one of the entries is not equal to the 0. Good. So I can check whether this non-trivial solution is a solution for the system of linear equations by just substituting values to the first and to the second equation. If I just substitute x1 with a 2 and x2 with a 1 to the first equation, it's going to be 2 minus 2 times to the 1, which is equal to the 0, which is true. And if I substitute this to the second equation, it's going to be 2 times to the 2 minus 4 times to the 1, which is also equal to the 0, which is again true. So what does the theorem tells you? That, hey, the solution x, which is going to be equal to the x bar times to the t, is also the solution. So essentially, 2, 1 times to the t, or 2t and t is also the solution. So we can check this, whether this is the solution, by just substituting this to the system of linear equations. So if you substitute x1 with a 2t and x2 with a t, what you have is, on the first equation, 2t minus 2 times to the t is equal to the 0, which is correct. And if I substitute this as a second equation, it's going to be 2 times to the 2t minus 4 times to the t, which is also equal to the 0 because 4 times minus 4t minus 4t is equal to the 0. You see, so it's like no matter what is the value of the t, this is still going to be the solution. For example, if the t is equal to 2, then x, the solution, the new solution, is going to be equal to 4 and 2. And this is the solution because if I just substitute this to here, to the first equation, or to here, to the second equation, it's going to be the solution. So if the t is equal to the 3, then x is going to be equal to the 6 and 3, which is still solution of the system of linear equations. So essentially, if I just substitute the x1 was a 6 and x2 was a 3, it's going to be the solution for the first equation and for the second equations. So this is what does it mean? Like if your system of linear equations has a non-trivial solution, then it's going to have infinitely many solutions. So for the homogeneous system of linear equations, there are always two possible cases, right? So in general, for the system of linear equations, there are three possible cases, like a unique solution, or infinitely many solutions, or no solution. While for the homogeneous system of linear equations, we're going to have only two possible ways, possible scenarios. Either there is only one solution, and this is going to be definitely the unique solution and the trivial solution when all of the variables are equal to the 0. Either it is going to have infinitely many solutions. So the last thing which I would like to talk with you in this video lecture is called the augmented matrix. So it is essentially, so augmented matrix is when we're going to put the another matrix on the top of the first one. So augmented matrix, which is essentially means putting something on the top of the another one. Okay. So what we're going to do is, if you remember, we've got a system of linear equations here. Okay. Oops. A1, so the case equations of a system of linear equations can be written as A1, 1x1 plus and so on plus A1k or A1n xn is equal to the B1 and so on. Oops, sorry. And so on. A k1 x1 plus and so on plus a kn xn is equal to the bk, so this is equal to the b1, is the system of linear equations. So if you remember, we used to have the coefficient matrix, we put them into one matrix, a1, 1, and so on, a1, n, and so on, a k1, and so on, a kn, and we put together all of the vectors from the second, so for the free coefficients to one matrix. Didn't we do this? Oh, not yet, right? Okay, so we can put all of the things to the matrices. So all of the coefficients, essentially, the coefficient before the x1, x2, and so on, xn is going to be copied to the first row. The coefficients from the x1 and so on, and the coefficient before the xn from the last equation is also going to be copied to the last row of this matrix. So all of the variables are going to be copied to this vector x, which is going to be the unknown vector, which is going to have the components x1, x2, and so on, xn. And all of the free coefficients, the coefficients on the right-hand side part, are going to be copied to another vector. So it was the components b1, b2, and so on, bk. And instead of writing down, so let me denote this matrix as the A matrix, for example, and instead of writing down the system of linear equations using the linear equations, we can write it down as the matrix. A times X is equal to the B. So this, the matrix equation. So, and what we are going to call as an augmented matrix, when we are going to put together this coefficient matrix A and the right-hand side part of this equations, the free vector, together to one matrix. So this is going to be the augmented matrix. So let's try to do an example and try to see what is the matrix equation of a system of linear equations and what is going to be the augmented matrix. So let's do an example. So let's say we're given a system of linear equations as 4x1 plus 3x2 minus x3 is equal to 9. 2x1 minus 5x2 plus 2x3 is equal to 2. x1 plus 6x2 minus 7x3 is equal to 0. How we can write down the system in a matrix form? In order to do this, I'm just simply going to copy those coefficients of the x1, x2, and x3 to the first row of the matrix. So this is going to be 4, 3, and minus 1. Then I'm just going to copy the coefficients of the x1, x2, and x3 from the second equation. It's going to be 2, minus 5, and 2. Then I'm going to do the same for the third equation. It's going to be 1, 6, and minus 7. So this is going to be multiplied to the vector x, which basically contains all the variables x1, x2, and x3. And this should be equal to the right-hand side part, which are just the coefficients without x1, x2, and x3, without variables, essentially. So that is why they are called the free coefficients. So it is going to be 9, 2, and 0. So this is the matrix form of the system of linear equations. So AX is equal to the B form. So what we're going to call as an augmented matrix is whenever I'm going to put A matrix and a B vector together. So I'm going to put here the virtual line, which basically doesn't exist. So let me put them together. So this is going to be 4, 3, minus 1, 9. 2, minus 5, 2, and 2. 1, 6, minus 7, and 0 is going to be called as an augmented matrix. So this is the coefficient matrix. So this is the right-hand side part, vector, B vector, and all together, so this matrix is going to be called as an augmented matrix. So essentially, everything which we discussed today is really important for us. So we're going to discuss how we can use a solution of a homogeneous system of linear equations in order to construct the solution spaces in general. And also, we're going to discuss how we can solve a system of linear equations algorithmically using so-called augmented matrices. So hopefully this lecture was very useful for you.